As we said before, we will, as promised, as they say, I'm just repeating myself, we will look at elemental cycles but only use carbon as an example. Again, just like water cycle, carbon cycle means you can track a molecule of carbon, an atom of carbon or a molecule of CO2, somehow tag it. Let's say you have designed a little robot that can do that, and you want to see where it's going, where it's coming out of, where it's going into photosynthesis maybe, and what it does. Does it go into the ocean? Does it go into land? Does it stay in the vegetation? Does it get eaten by a cow as shown here, and so on and so forth. So that's the cycle that we worry about. Obviously, every time you do a cycle, you want to have some sense of how long things stay in the tank or the storage. Remember, we talked about storage of water and flow of water. Similarly, you have storage of carbon or CO2 and flow of CO2. And if you're old enough and you're reading about carbon cycle or looking at the numbers, you often see carbon storage mentioned as carbon amount, let's say in 10 to the 12 tons, something like gigatons of carbon, let's say per year. But sometimes you say gigaton CO2 per year, and you know how to convert carbon to CO2. You just take the molecular weights and multiply. So if you want to go from carbon to carbon dioxide, you will need to multiply by 3.73 or some such number. Make sure exactly what it is. And sometimes you will also hear something called CO2 equivalent. Okay, and you can actually understand this a little bit. If you don't understand the details, don't worry about it. But when you see CO2 equivalent, don't be shocked, and just remember this much. We talked about greenhouse gases. We said CO2 is a dominant one, water vapor is a greenhouse gas, methane is a greenhouse gas, N2O is a greenhouse gas, and there are others like the refrigerants, chlorofluorocarbon and hydrochlorofluorocarbons, and so on and so forth. They are also greenhouse gases. Each greenhouse gas has a different level of ability to trap the outgoing thermal energy, but we can use some clever tricks to see how we can convert them all in terms of CO2. CO2 is got a global warming or a thermal radiation blocking capability of 1. How does methane compare? Is methane the same as CO2 or it's higher? If it's stronger, how much stronger is it? So the number is something like 25 for methane. So methane is 25 times as strong a greenhouse gas. It is capable of blocking thermal radiation 25 times as much as CO2. Similarly, other greenhouse gases will have different abilities compared to CO2. So when we convert all of them, we can measure all of greenhouse gases in the cycle and say CO2 equivalent. Okay, now you are ready to understand that part. So let's come back to CO2, but you can easily switch to carbon, because now you know that you just multiply by a number or divide by a number and you can go between CO2, carbon dioxide and carbon. In the simplest sense, this is a little too simple for, let's say, a 12th grade student or an undergraduate or maybe even 7th, 8th grade students. But if you're a kid, then you know that the ocean is taking up some, so there is some CO2 in the atmosphere. There has always been. Since the beginning of the solar system, there have been many gases in the atmosphere. The continents looked different, as we know from looking at the continental distribution during the dinosaurs, and we said India has moved across from the southern hemisphere into the northern hemisphere and is pushing into Asia and so on and so forth. But at some point the mixture of gases in the atmosphere was different. We can do some detective work to find out that methane may have been the most important greenhouse gas when Earth just got formed after the Sun, or around the same time, and over time CO2 became the more dominant greenhouse gas, then came the plants, then came a lot of things, mountain building and so on and so forth, and CO2 has remained in the atmosphere for billions of years. I'm just getting dramatic here, maybe to help you pay attention. Okay, so that CO2 naturally occurring in the atmosphere has always been there. It has gone up and gone down because with ice ages you reduce the carbon dioxide in the atmosphere because vegetation is covered by ice, oceans are covered by ice, so CO2 is hidden. When the ice melts away, like now, you know, the CO2 comes out. So if you think about the last ice age, CO2 was lower, and then as the ice age ended about 10,000 years ago, it jumped up naturally. Okay, then we started to do things to increase it more rapidly. Okay, so we'll look at a figure on how we measure this. So right now CO2 is going into the ocean from the atmosphere, and CO2 is easily dissolved in water, which is why we have these sparkling water and Coke and Pepsi and Thumbs Up and so on and so forth, where CO2 is dissolved into the water, and how much dissolves depends on the temperature of the water. Cold water can dissolve more CO2, and if you put it under pressure, then it can stay there. That's why you have the bottles or cans of carbonated drinks like sparkling water, Coke and beer. I don't want to talk about beer. They are sealed. If you open them, immediately CO2 begins to fly out of the dissolved water, because how much remains inside depends on, if you don't know chemistry, you can understand this, otherwise do not worry about it, something called the partial pressure of CO2. Atmosphere is made up of nitrogen, oxygen, argon, and then lots of other gases, and there is a tiny amount of CO2, and each gas in a volume will exert some pressure. Partial pressure is just how much is exerted by CO2 itself, and in the ocean also, when CO2 is dissolved, it has a partial pressure. So the difference in the partial pressure determines whether CO2 will go in or go out. Okay, on average over the whole globe, CO2 is going into the ocean. There are some places where it goes up and some places where it comes out, but when you average, it's taking in about 25% of the CO2 that we are producing in addition to what was already there. How do you think about this? When you open the Coke can, immediately it begins to evaporate because the partial pressure of CO2 in the Coke is higher. It's been dissolved into it, kept under pressure, but when you reduce the pressure, the partial pressure of CO2 in the Coke is higher than the air above that you expose it to, so CO2 immediately begins to flow out. CO2 doesn't go into the water, into Coke, if you just leave it open. It just goes out. Okay, there will be some left, which depends on the partial pressure again. So that's called a sink. Wherever CO2 is going in, like this photosynthesis here, plants are taking up CO2. Are they always keeping it? Well, it depends. During the photosynthesis season, when the sun comes up, as we saw in the vegetation animation in the last podcast, CO2 is going in. But remember that plants are also breathing. At night, during the day they are photosynthesizing and breathing. At night they are not photosynthesizing and they are breathing, so they are releasing CO2. But as long as they are building leaves and trunks and roots and so on, they are storing some carbon, or they are locking it up, so they are sinks of carbon. So this is they are sinks. So sinks into the ocean, sinks into the vegetation, but there are lots of sources of CO2. All the animals that eat something, like cows and us, we eat things and we breathe out CO2, right? So plant and animal respiration. Photosynthesis is where you are locking up CO2, producing hydrocarbon, sugar, carbohydrate, and so on. But when you consume that carbohydrate and sugar and you respire it, which means you burn it to produce energy, our energy comes from eating those hydrocarbons, then you are producing CO2. So that's a source source of CO2. So plants can also produce CO2 from respiration. So they are not just fixing carbon, it's called fixing carbon when they take it up and lock it up, right? And of course there are fossil fuels which we are digging out of the earth that formed long time ago for various reasons, and we are burning them, which means we are releasing the carbon that's locked in them. Imagine that the plant has produced carbohydrate and hydrocarbon. It gets buried somehow because of an earthquake, because of an ice age with ice on top and so on. And that can over time, if it stays down long enough under pressure and so on, can become fossil fuel unless somebody else eats it underground like termites or so. Then it becomes fossil fuel like coal, petrol, gas, etc. And we dig it up and burn it. So that is a source of CO2 to the atmosphere. Okay, and there are things that are decaying. If you throw some food outside, it's going to be respired by bacteria and microbes which eat them, or some animal will eat it, some bird will eat it. If you put rice outside, a crow is going to come and eat it, and then the crow is going to digest the rice and release CO2. So there are various ways in which CO2 gets released after it's been combined with water and CO2 to produce hydrocarbons. Okay, so combustion. We are producing energy by burning hydrocarbons like coal, petrol, gas, biomass. We are burning trees themselves and so on. So that is a source of CO2. So scientists sit down and figure out how much CO2 was going in and coming out before the Industrial Revolution, when we were not so many in number, population was smaller, and we were doing things, agriculture, fossil fuel burning in terms of biomass, we were burning sticks and so on, but not at such a large scale. So at some point we began to burn more and more because we are producing more and more things. We are driving cars, we are flying in airplanes and driving motorcycles and so on. Everything needs energy, everything is coming from burning things. Now we have more and more solar and wind energy, but we are read about carbon cycle now. So when we begin to emit, we are perturbing the natural sinks and sources of carbon, and we are beginning to increase the amount of CO2 and carbon in the atmosphere, and of course in the ocean as well, and in the soil, right? And that is what is the increasing greenhouse gas that traps the thermal radiation and causes global warming. And once there is global warming, temperature increases, it takes, atmosphere, warm atmosphere is thirsty, so it wants more moisture. So plants, when they open the stomata to capture CO2 to do photosynthesis, they have to be careful how long they open, because they want to take enough CO2 but not lose too much water they brought up with hard work from the root. But if the atmosphere is warm, it wants more moisture, then it may take out more moisture, because again, it depends on the partial pressure difference within the leaf and in the atmosphere. That's called vapor pressure deficit. But let's not worry about that. So all these details matter as to how CO2 is going around and getting cycled, and where it is going in is important, but how long it goes in is also important. Now you link it back to your ocean circulation. We said there is wind driven circulation which is near the surface, ocean is being dragged down by the winds, but there are regions where the water is getting heavier and sinking, and we said when the water sinks, it takes whatever is in the air that is mixing with the surface water with it to the bottom. So CO2 is also going into the ocean, and it can go down and stay for a long time. As we said, the water doesn't come up back again for hundreds of years, so that also matters. So we want CO2 to go in as much as possible somewhere into vegetation, forests, ocean, soil and so on, and we want it to stay there for a long time. Okay, so there are different time periods for which it stays there. Ocean can take it away for a long time. Soil is very shallow, doesn't put it away for so long because we do some agriculture, or forests burn down and we cut down forests for wood and for building houses and so on and so forth. So all these things are sources, sinks and storages of carbon. How long things get stored in a tank, in a reservoir, tends to be called residence time. Okay, in the atmosphere, how long does it stay? We know that it stays for a few hundred years. In the ocean, it can stay for much longer. In the soil, it can stay longer if it's not perturbed. In the trees, it can stay long if the tree stays alive. Some trees can live very long time, thousands of years. There is some details as to why they can do that, but that's the main thing. How do we know? Let's say we did some detective work and found out that CO2 is increasing in the atmosphere, and somebody says, let's say your grandmother asks you, but how do you know that that CO2 is coming from us burning fossil fuels, coal, for example? And there are ways to do that, more detective work. Okay, so just remember there are isotopes. So fossil fuels that are buried for a long time have a different level of certain carbon isotopes. So if you keep putting it back into the atmosphere, the isotope concentration in the atmosphere of CO2 in the atmosphere begins to change, and we can measure it using some nice chemistry lab experiments and machines and say that, look, this is not natural CO2. We are producing it by burning fossil fuels. And when you burn, what do? You use oxygen. So you can also measure oxygen is decreasing slightly. Nothing to worry about, because there is so much oxygen that even if we burn all the forests, there will still not be a problem of breathing. We'll have enough oxygen, but there will be a lot of other problems, right? Pollution, air quality, and so on. It'll be harder to breathe, not because there's not enough oxygen, but because there is too much pollution. And of course you want photosynthesis, food, and so on, right? So let's leave this here. I use this figure to explain a lot of things, because these are concepts that don't need numbers and they don't need fancy figures. So this is a bit long, but it's a nice story, so you should listen to it. Now we'll come back and look at some numbers, because we cannot get away from numbers, and we'll mention the residence time of carbon dioxide and some other properties of carbon dioxide as well. Okay, so see you again in the next podcast to continue our discussion on the carbon cycle.